Thunderstorms develop when the atmosphere is unstable. This is when warm air exists underneath much cooler air. As the warm air rises, it cools and condenses, forming small droplets of water. If there is enough instability in the air, the updraft of warm air is rapid and the water vapor will quickly form a cumulonimbus cloud. Typically, these clouds can form in under an hour. As the warm air continues to rise, the water droplets combine to create larger droplets which freeze to form ice crystals. As a result of circulating air in the clouds, water freezes on the surface of the droplet or crystal. Eventually, the droplets become too heavy to be supported by the under updrafts of air and then fall as hail. As hail moves within the cloud, it picks up a negative charge by rubbing against smaller positively charged ice crystals. A negative charge forms at the base of the cloud where the hail collects, while the lighter air crystals remain near the top of the cloud and create a positive charge. The negative charge is attracted to the Earth's surface and other clouds and objects. When the attraction becomes too strong, the positive and negative charges come together or discharge to balance the difference in a flash of lightning, sometimes known as lightning strike or lightning bolt. The rapid expansion and heating of air caused by lightning produces the accompanying loud clap of thunder.
Why is it important to predict? About 2,360 Indians die every year on an average due to lightning strikes. Our analysis of data from the National Crime Reports Bureau since 2001. Over 40,000 lives have been lost to lightning since 2001. In 1963, Pan Am Flight 2014 got re and crashed after being struck by lightning, killing all 81 people, passengers, and crew. In 1987, lightning destroyed an Atlas Sanctuary rocket during launch. Lightning warnings may be prevented such tragedies. Luminous effect is one of the demerit of lightning. A lightning strike nearby violating sanitizes the retina of an observer. The eye is dazzled and vision is lost for several long seconds. In India, lightning has remained the largest single cause of death due to natural disaster every year since 2002. Here are two graphs. The first one shows death versus year. We can see the number of deaths due to lightning increases per year on an average. The second one is the state-wise cases of death due to lightning. Here are some of the terminology which you should know before moving to the methods. The first one is electric field mills, known as EFMS. Basically, they are instruments that measure the voltage per meter, V per meter of the nearby atmosphere. EFMS measure at a rate of 50 Hz with values ranging from approximately 15,000 volt per meter to 15 lakhs per volt per meter. The two primary categories that must be made for EFMS are first one is do not launch for 15 minutes after the absolute value of any electric field measurement at the surface within 5 nanometer of the path has been greater than 1500 volt per meter. The second one is do not launch for 15 minutes after the absolute value of any electric field measurement at the surface within 5 nanometer of the path has been greater than 1000 volt per meter. The second one is statistic window. This is basically a time period over which EFMS readings may be summarized. The second one is measurement windows. MW, the amount of the time used by a model to predict a lightning event. The third one is prediction window, PW, the time window in which lightning is predicted. The fourth one is warning window, that is WW. WW is so named because in a real world lightning event, this is the amount of warning that one can expect to have before a lightning event occur. I also attached a figure where you can see at once all the four windows, that is statistics window, measurement windows, warning window, and prediction window. AOC, the area of concern. The shape of this area may be circular, rectangular, or elliptical. The total area covered by the AOC may range greatly depending on the search and the design decisions. Then we have the next term, that is true positive. True positive is basically the case when a model prediction a lightning event and it's lightning and it is actual a lightning event. False negative is a case when a model predicts no lightning, but in reality lightning occurs. PPR, also known as probability of detection, heat rate, sensitivity, or recall. It describes how well a model does at accurately predicting true lightning events. Then we have FP or false alarm, a model that predicts only lightning events result in a large number of FPs, which would stop all space flights operation and not be realistic. TNR, it is the effectiveness of a model to accurately not warn of a lightning event. Then TSS, this statistic ensures heavily weighting the TPA, resulting in it becoming equal to TPM when a model is attempting to predict rare events. This could be problematic for lightning events. The OUI uses the TSS in addition to TPR and FDR and weights these three statistics to calculate a metric with a maximum value of 0.83 being the best possible model. The K index or George's index is a measure of thunderstorm potential in meteorology. Here is a quick recap of a machine learning model, that is logistic regression. Logistic regression is a classification algorithm. It is used to predict a binary outcome, that is 1 or 0, yes or no, true or false, given a set of independent variables. In our case, 1 means lightning happened and 0 means does not. There's a right hand side, there's a graph. It is an S-shaped curve that can be take any real valued number and mapped it into a value between 0 and 1, but never exactly at those limits. Artificial neural networks are machine learning methods loosely inspired by the neural synapses of the brain. The layers are made up of nodes. A node is just a place where computation happens, loosely patterned on a neuron in the human brain which fires when it encounters sufficient stimuli. A node combines input from the data with a set of coefficients or weight that either amplify or dampen that input, thereby assigning significance to inputs with regard to the task the algorithm is trying to learn. For example, which input is most helpful is classifying data without error. These input weight products are summed and then the sum is passed through the node's so-called activation function to determine whether or and to what extent this signal should process further through the network to affect the ultimate outcome. Say an act of classification. If the signal passes through, the network has been activated. Here you can see mathematical interpretation of what I just mentioned. This is the general architecture of a neural network. Now we can discuss different methods to predict lightning and thunderstorm. Let's start with the method 1. So here's the description of method 1. In the method 1, the model uses logistic regression. The variables used are basically 4 variables are used. The first one is 13-minute maximum value across all EFMS, global positioning system, that is GPS, integrated precipitation water vapor, IPWB data, change of GPS IPWB over a 9-hour period, and the K index values. In this method, the statistic windows used of 30 minutes, the MW is equal to 30 minutes, the WW is equal to 90 minutes, and the PW, that is the predicted window, is of 13.5 hours. The threshold is of 0.7, means if the values comes out to be greater than 0.7, then it's considered to be a lightning event, and if it comes to be less than 0.7, then it is considered to be a non-lightning event. We have the area of concern of 20 nanometer radius. The output is basically the probability of lightning known as GPS lightning index. In the right, we can see the confusion matrix of the method, where we get lightning versus the predicted lightning, non-lightning versus the predicted non-lightning. Let's move to the second method, that is method 2. In this method, the model used is same as earlier, that is logistic regression, with different 4 variables are used. The first one is 13-minute change in GPS perceptible water. The second one is 7.5 hour in GPS perceptible water. The third one is current perceptible water, and the fourth one is K index values. Uh, Unlike what we discussed in method 1, here the SW and MW is not fixed, not a fixed value. It varies. The warning window is of 30 minutes and PW is 0, which means the predictable prediction window is just get started after MW. The area of concern is of radius 5 nanometer. The output is probability of lightning known as GPS lightning index. The 2-hour forecast interval spaces a warning window of 30 minutes, with the remaining 90 minutes accounting for real world expected delays between measurement and the warning being issued. Here is the method 3.
In method 3, basically we integrated the EFMS data. Before we discussed one in method 1 and 2, in which EFMS data are not considered while when we are using the model of logistic regression. But in this model number 3, we integrated the EFMS data in order to better understand how EFMS could contribute to lightning predictions method, a threshold method that predicting lightning if the SW is equal to 10 second and SW is equal to 60 second, means of two EFMS simultaneously read greater than a threshold. It is considered to be a lightning. If the mean of the two reading has the value less than threshold, it considered to be non-lightning event. By varying the size of the AOC and the orientation or distribution of EFMS around the AOC may improve the result. In the left table, you can see different AOC parameters of different models that we discussed till now. And the right contains the time window parameters of different model, which consist all the windows, that is statistics windows, measure window, warning windows, and prediction window. This is the summary of the result that we got from different models. It consists TPR, FPR, FDR, and OUI of the result that we got from different models. Consider weather data in which the same way that sentence structures are similar throughout a story and that given a set of words limits the next word to follow. Weather is dependent on what has happened in a region in the past and what has immediately happened leading to a moment in time. If the same information was presented as a large array of data consisting of many sensors placed throughout a region, the data may appear more similar to a hyperspectral image. This type of problem is more suited to a CNN. By combining this idea, CRNN is born. The LDR array records lightning axis and is compressed of 9 sensors surrounding the KSC. The LDR array detects lightning axis up to 100 km from the KSC, providing the precise location in X, Y, and Z distances from the center, and the time of the lightning event using chi-squared minimization of the estimation of the sensors. The LDR lightning of the with the EFM voltage per meter measurements to produce a dataset identifying the state of the atmosphere at the time of the lightning event. Now, how much data we are dealing with? Let there are 31 EFMS present. The EFMS data one pre-process were organized into a folder for each day of data, meaning that folder contained 48 folders corresponding to every 30 minutes time period that made up a 24-hour day. Each of these folders contained 31 files of data, one file for each of the 31 EFMS. Thus, for a complete day of data, there were 31 into 48, that is 1488 data files, each with 90,000 observations, 30 minutes worth of 50 Hz reading. Now, move to data creation. The first action taken to clean the data was to remove data from faulty sensors. Several files contain multiple EFMS reading with the same date and time. Only the first occurring instances of this repeated data points were kept. If the sum total of time of this SW is totaled more than 1 hour, then the entire day was removed from the analysis. Additionally, any day that didn't contain a lightning event within the AOC was excluded from the analysis. in the EFM data if only mean and variance were measured. Important information about the nature of the atmosphere may be missed. For this reason, all four statistics are calculated being several time periods to ensure the most accurate description of the electric gradient of the atmosphere is obtained. The fifth channel was a binary value that indicated if insufficient data was available to calculate the summary statistics. If there were less than four values within a SW, then attempting to calculate the statistics would result in a NaN for at least one of the statistics. The corresponding fifth channel would be set to 0, indicating missed data. Two circular AOCs were established with radii of 5 miles and 10 miles, both centered at the LDR center. Two LDR datasets, one for each AOC. By comparing the time of the lightning event to the EFM statistic window time period, a response of 0 or 1 was given to the corresponding observation. The response was set to 1 if a lightning event occurred within the AOC in the SW and 0 otherwise. These values are extremely large and could cause exploding gradients in an ANN. To prevent this and to maximize the likelihood of training, all statistics were mean max scaled. LDR datasets allowed for the creation of the response variable by the determining if a lightning event occurred during the time period over which the summary statistics were calculated. 1 if yes, 0 if no. This resulted in 6 distinct statistic datasets, 3 SWS into 2 AOC, 6 datasets. To appropriately evaluate the effectiveness of the model, the data was split into training, validation, and test dataset by randomly selecting 70% of the day datasets for training, 15% for validation, and 15% for training.
Initially, model selection began with a single LSTM layer with 4 neurons and a single neuron dense output layer with a sigmoid activation function. Adam was chosen as the optimizer and binary cross entropy as the loss function for all iterations of the model, selection process, and the final model. This initial was able to achieve a 65% accuracy on the training dataset, which indicate it didn't have sufficient capacity to overfit to the training data. To optimize our model, two additional LSTM layers were added, each with 16 memory cells, and our training accuracy jumped to 76%. A number of different initial learning rates were used, but the best performance was seen when using an initial rate of 0.1 decaying gradually. A convolutional layer was added before the LSTM layers to attempt the capture pattern of change of each EFMs across small windows of time. A convolution layer across the EFMs were used to capture the correlation of EFMS across a time period. 8 kernels of size 3,1 were used with same padding and a rectified linear unit ReLU activation and function. Above optimization method increased the accuracy to 86%. A convolution layer across the EFMS are used to capture the correlation of the EFMS across a time period. 8 kernels of size 1,30 were used with valid paddling and a ReLU activation function. This saw an improvement to 93% by increasing the number of kernels on all the convolution layers to 16 and decreasing the initial learning rate to 0.01. The final configuration of the model was established. It achieved a 96% accuracy in the training data. In the right I try to show CRNN architecture, and in the bottom we try to show the confusion metric that I got, which shows the maximum OUI was obtained at a threshold of 0.547. The model achieved an overall accuracy of 96% with a true positive rate TPR of 77.6%, a probability of false detection POFD of 8.3%, and an OUI of 53.9%.